We are honored today to be joined by Guido Imbens, the Applied Econometrics Professor at the Stanford Graduate School of Business and winner of the 2021 Nobel Prize in Economics. And we are very excited. Okay. The subject of his talk today is multiple randomization designs, in which he will share about a new class of A/B experiments. Before we get to the talk, let me share a bit about Guido. Professor Imbens was born in the Netherlands, where he attended Erasmus University, Rotterdam. And then he got his PhD at Brown University, followed by being a professor at Harvard, and then UCLA, Berkeley, and then back to Harvard, before he joined Stanford GSB's economics department in 2012. Among his numerous accomplishments are publishing a causal inference textbook, joint with Don Rubin, professor of statistics at Harvard. And in 2019, he became editor of Econometrica, one of the leading economics journals. Last year, he won the Nobel Prize for methodological contributions to the analysis of causal relationships, which he shared with Josh Angrist, professor at MIT, and best man at his wedding, as well as David Card at Berkeley. He is married to his frequent co-author, Susan Athey. He is the proud father of 3 kids, chief caretaker of several chickens. Thank you, and please join me in giving a warm welcome to Professor Guido Imbens.
Thanks, Rose. Thanks very much for the very kind introduction. It's great to be here. So I'm going to talk a little bit about research. Actually, I'm doing. Let me then go on to the. I'm particularly excited to be talking here because I think there's this huge amount of very interesting work going on in the tech companies here on experimental designs and causal inference. Actually, remember years ago, 2008, there was some discussion in the economics literature where Angus Deaton was arguing that all this focus on experimentation wasn't really very useful. Experiments were no better than observational studies, and this was all overblown. And I wrote a comment on that, and then Steve Levitt kind of wrote on his blog that, well, he sort of agreed with Deaton, he sort of agreed with what I wrote, but he didn't think there was all that much point to it because he thought experiments were just really simple, and there wasn't really that much point in people spending a lot of time trying to think very hard about how to do experimentation and how to analyze the experiments. I think that was actually kind of the worst part of the whole discussion, because I think now and what's happening at the tech companies shows it's actually doing experiments right in these settings in the tech companies is actually really challenging and really incredibly interesting. So there's really interesting work going on in these places. And there's really interesting questions coming up there that were not there kind of in the traditional agricultural experiments where Fisher and Neyman were doing these agricultural experiments, putting fertilizer A here, fertilizer B there, and then waiting a year till the end of the season to see what the effects were. And so what I want to talk about specifically here is a set of methods I've been working on with some people at Amazon on settings where we worried that standard randomized experiments are going to have biases because of spillovers, because of interactions between units. And so let me just make them very specific, and I'm going to think of a very stylized example. So suppose we're thinking about offering customers more information about a product in a setting where customers can buy products, you can buy multiple products over some period of time. And we're thinking about changing a little bit the way these interactions take place, maybe in the form of giving more information to customers when they look at products. And so how could we do an experiment to evaluate the effect of, to estimate the effect of such a change? And so conventional A/B testing type experiment, we could do two things. We could randomize the products, or we could randomize the customers. And so if we have 8 products here, we could assign products 1, 3, 4, and 8 to the control group, and the products 2, 5, 6, and 7 to the treatment group. And then we could evaluate the experiment by looking at the average outcomes for the treated products and the control products. Or we could randomize the customers. So here we have 5 customers, and customers 2 and 5 are in the control group, and we could compare outcomes for treated customers and control customers. But in many cases, we would be worried that simply randomizing products or randomizing customers wouldn't work, wouldn't give us an estimate of what we're interested in, namely, what would be the average outcome if everybody was exposed to the treatment versus nobody was exposed to the treatment. And the reason is that there may be spillovers. It may be that there's cannibalization, that if you randomize the products, the customers are going to switch from control products to treated products to similar treated products. And if we randomize customers, that may affect how sellers behave in a way that invalidates the experiment, that doesn't make it estimate what would happen if everybody was exposed to the treatment versus nobody was exposed to the treatment. And so the basic idea here is to think of the experiment as not choosing a factor of the indicators for assignment to the treatment group and the control group, but to think of the experiment as choosing a matrix of assignments to the treatment and control group. So, of course, you can't do that in every setting. In particular, in a sort of regular brick and mortar store, you can't do that. If 2 people go to the store at the same time, they get the same experience. They don't see a different display, and certainly they wouldn't see different prices. But in online settings, there's lots of parts of the experience you could actually change between pairs of customers and products. You can kind of change how much information you give them about the product, or how many other things you show at the same time. And so you can think in that case of doing an experiment where you choose all the entries in this matrix, because you can vary the experience within a customer as well as within a product. And so from that perspective, the 2 experiments I just described, the customer experiment would be one where you limit yourself to choosing a matrix where every column in that matrix is the same. And a product experiment would be an experiment where you choose every row of that matrix to be the same. Because once you write it this way, it's sort of very clear that that's actually an artificial restriction, and that you could do much more. You could choose a matrix in a relatively unrestricted way, and there may be much more, there's going to be more information in that, and you may learn more effectively even in the absence of spillovers, you may learn more effectively what the effect of the treatment is. So rather than see it as a choice between either doing a customer experiment or doing a product experiment, I want you to think of the choices being choosing a distribution for this matrix, choosing a distribution for the set of binary indicators to the treatment. So this is still in a setting, but it's just a binary treatment. You can kind of generalize that, but I don't want to go there here. You're still choosing a binary treatment, but you're choosing it at the level of the pair customer product rather than at the customer level or the product level. And so, for example, we could, and the simplest version of that is you randomly select a set of customers, you randomly select a set of products, and only the selected product customer pairs are exposed to the treatment, and everybody else, every other pair, is assigned to the control group. And now you can compare, you can do things that you can't do in a customer experiment or a product experiment, because now you have 3 different sets of customer product pairs that ex ante are the same, because we actually randomly selected the customers and the products, but exposed have different experiences. So for example, if you look at the green C's, those are customer product pairs where the customers are sometimes exposed to the treatment. And so if there's cannibalization, if people switch from the controlled to treated products, the green Cs would typically have different outcomes from the red Cs, where the customer and products are both always in the control group. And so this type of experiment is going to allow you to make comparisons that allow you to get a handle on whether actually these spillovers are present. So you're going to be able to learn more from such an experiment than you would from a customer or product experiment. And in addition, you're going to be able to learn the standard things more efficiently, even in the absence of spillovers, because now you can use customers as their own controls and products as their own controls. And if there's a lot of heterogeneity there, these would be more efficient. But the big thing is really that by creating these ex-ante comparable control groups, you're going to be able to directly get estimates of the magnitude and the presence of spillovers. Now you can do much more complex things, and so here is one design kind of that we're thinking about, and we're working through some of the implications of, where you start by randomizing the products into two groups, here denoted by A and B. And then for one experiment, for one set of products, we do a customer experiment and we randomize the customers to the treatment group or the control group. And for the other set of products, we do a product experiment. And now, again, we're going to get three different sets of customer product pairs that are in the control group, but have different experiences. But we're also going to get three different sets of treated pairs that have different experiences. And now, kind of from all these comparisons, we're going to be able to learn something about direct effects of the treatment and possibly indirect effects coming through the sellers responding in different ways to the fraction of individuals being treated. If the treatment makes the products more attractive, then the sellers may respond by changing the other aspects of the product to capture that. And so we're going to be able to learn much more from this type of experiment than from standard experiments. And so what we then do in the paper, and I'm not going to go into a huge amount of detail here, but we can look at different targets. We may be interested purely in the overall average effect if everybody was exposed to the treatment versus nobody was. That's going to be tricky here because we can't actually ever see that. And so we're going to need to put some limits, some structure on the interactions to be able to extrapolate from the things we learn from this type of design to figuring out what would happen if everybody was exposed to the treatment. We can try to learn something about the magnitude of the spillovers. Then second question is, how do we actually choose what the distribution is of the assignments? I gave you two examples, kind of the simple double randomization design and this kind of more complex one, but there's lots of things we can do. And we don't actually really know, we're not very far along in figuring out what would be an effective way of doing the design, because it depends a lot on what the objectives are and how big the spillovers are. And so the questions are going to be much trickier than in a simple A/B test, where typically the optimal thing is just dividing things 50-50 in a treatment and a control group. Then the question is how we actually estimate things. It's going to be easy to figure out how to estimate the average outcome for these different groups, but how to translate that into the objects we're actually interested in is going to be more complex. And finally, we want to do inference in the same way we do in standard experiments, relying purely on the randomization. And there we do have a handle on how to do some of that. But so in some sense, this is kind of the slides up to this point are the most important parts of the talk. the insight is really that in many of these cases where we think of there being multiple sides to a platform where there's multiple populations that interact on a platform, thinking of experimentation not just as choosing one of these sides and randomizing them, but thinking about randomizing both, and it could even be more than two sides, but randomizing both at the same time, or having some randomization on both sides can be very helpful in figuring out whether any of these spillovers are present and giving you a handle on how to actually estimate the magnitude of those things. So I didn't actually keep track of when I started. How much time are you giving me, Rose? I can keep going. Very good. So just give me some notice. So let me now. So again, kind of the first 6 slides were what I really wanted to go to. Kind of the big insight from my perspective was kind of the realization that it's not a choice between doing experimentation on one side of these platforms or the other, but that you can do both at the same time. But what's going to be tricky then is that you are going to need to put some structure on how these interactions, how these spillovers take place to make some progress. But in all of these marketplaces, the spillovers and interactions are intrinsic to the nature of these platforms. Treating one customer for a particular product may have an effect on the outcome for some other customer, because the seller side of the platform may respond. Treating one product for a particular customer may have an effect on the outcome for another product, because the customers may choose between these things, and the treatment may make some products more effective. And so the standard experiments ignore that, and they don't give you the opportunity to actually assess the presence of these spillovers. And this type of experiment is going to allow us to get a handle on those things. So to make that a little bit more precise, suppose we have a setting where we have capital I customers, capital J products. And the key thing is that we measure both the outcome at the product customer pair, and we can assign the treatment, we can manipulate the treatment at the level of the customer product pair. And suppose what we're interested in is what the effect is of exposing everybody to the treatment versus nobody. And so let me then look at 2 specific examples of that and go into a bit more detail there. First thing is that even if there's no spillovers at all, even if we're confident that there's no interactions between either customers or products, we can do much better than having a product experiment or a customer experiment by using designs that are balanced within customers and products. So here, every customer is in the treatment group for 4 of the products, and in the control group for 4 of the products. And every product is in the treatment group for 2 of the customers, and in the control group for the 2 other customers. And so in the absence of spillovers, we could just estimate the average effect of the intervention here by comparing average outcomes for treated pairs and control pairs. And if you put some structure on the outcomes, if you assume there's a customer effect and a product effect, you can see very clearly that by doing the completely randomized design, you get the variance proportional to the 1 over the product of the number of customers and products, where for either the customer or the product experiment, the variance is proportional to just 1 of the sample sizes. So you can get much more precise estimates of the effects of interest using these designs. But the more interesting case is settings where you are actually interested in spillovers, where you're concerned about spillovers. And so let's look in a little bit more detail at what we call this simple double randomization design, where we select a set of customers, select a set of products, and then treat the selected customer product pairs. And so now we have 4 types of customer product pairs. We have what we call the consistent controls. Those are pairs of customer products where both the products and the customers are always in the control group. Then we have the treated pairs. That's just the pairs of customer products that are in the treatment group. And then we have these 2 intermediate groups. The inconsistent customer controls are customers who are sometimes in the treatment group and sometimes in the control group, and products that are in the control group. So those are the green C's here. And we have the inconsistent product controls, where the products are sometimes in the treatment group and sometimes in the control group. And so let's kind of think a little bit about the different comparisons between different groups. The first one, where we just compare all the treated versus all the controls, isn't actually all that interesting. What is much more interesting is to compare the treated versus consistent controls. And if we're assuming, and that's kind of a big assumption here, if we're assuming that the spillovers only take place within a row or within a column, so that customers' products are only affected by what happens to other products for the same customer or other customers for the same product, then the overall effect of the treatment can be estimated by comparing the treated versus the consistent controls. We can also compare different control groups. If we compare the blue C's, the inconsistent products versus the consistent controls, we learn something about the spillovers within products. If sellers respond to the treatment, so if sellers respond, say, to the increased demand for the product because of some of the customers being treated, if they change other parts of the experience, that would show up in a difference between the average outcomes for the blue C's and the red C's. Similarly, but then in the other direction, if we compare the inconsistent customers with the consistent controls, we learn something about the spillovers within customers. If customers change which products they purchase as a result of the treatment, say there's more information there now that makes the products more attractive, they just switch from control products to the treated products, that would show up in differences between the average outcome for the green controls, the inconsistent controls, and the consistent controls. We can also try to separate out the total effect of the treatment from these spillover effects by looking at this difference in differences type comparison, where we subtract the difference between the treated and the inconsistent product controls from the difference between the inconsistent customers and the consistent controls. And that gives us an estimate of the direct effect of the treatment, where you take out the spillovers coming through other customers or other products being treated. So this is kind of just to illustrate that by using this type of experiment, we can learn much more. There's a much richer set of answers we can get about what the effect of the treatment is and how the effect of the treatment works through spillovers on both within products and within customers. And sort of clear, you can make this design much richer. You could have more variation in the fraction treated products for each customer. You get more variation in the fraction treated customers for each product. And the optimality of various designs is going to depend on what the nature of the spillovers are, what the spillovers are you're most concerned with. So there's a lot more detail in the paper about how to actually do that and how to get how to do inference for these various comparisons and how to extrapolate them to the different things we're interested in. So the bottom line, and again, there's a paper on arXiv that has all the details for this, but the key thing to take away is that if we doing experimentation, like many of us do, in settings where there's really multiple populations, we can do much richer things than the type of thing Fisher and Neyman were doing in these agricultural settings, or the type of things people do in medical drug trials. We can try to get a handle on these spillovers by exploiting these much more complex designs. And that opens up a lot of questions about how to do the optimal design of these experiments, opens up a lot of questions about how to actually analyze these experiments, how to model the inference, and most importantly, it kind of forces you to actually think about models for these spillovers. You can't, randomized experiments are great if we know for sure there's no spillovers. But once you relax that, you cannot relax it completely to allow for completely general spillovers. You need to put some structure on that. And so randomization is not going to solve all the problems here. We need to actually think very carefully about how these spillovers arise, what the limitations are, what groups we can compare to minimize or get a handle on the magnitude of these spillovers. And so I think there's going to be a lot of additional interesting work in this area. Some of my colleagues at Stanford are working on designs kind of where sometimes the spillovers arise purely through a price mechanism. Stefan Wager has done some work with Zhang Xu on that. And I think there's just going to be a lot of additional experimental designs that try to figure out how to get a handle on these spillovers. So let me stop here